characteristics of instruments. So we asked for linearity, repeatability or time invariance, then we asked for low drift. In drift also we asked for zero, we discussed about zero drift and sensitivity drift. Then we saw what you mean by dead band, it should be low. Then we saw about resolution, this should be high. We discussed about precision and accuracy. These were the characteristics we discussed, and we also saw about the classification of the instruments. That is going to be very, very important. We classified them as indicating, integrating and recording type of instruments. In indicating instruments we saw examples also. I am repeating because this question has come in gate. In indicating instruments, all your voltmeter, ammeter, wattmeter, speedometer, all these things are examples of indicating type of instruments. In integrating we saw about energy meter. The example will be energy meter and odometer, which measures the distance on your vehicles. Recording can be XY plotters, CRO, your ECG machine, all these things. So remember, in case of indicating, it is going to indicate the instantaneous value. In case of integrating, it is accumulated value over time. And in case of recording instruments, it is going to be variation of quantity, variation of the quantity. It may be variation of one quantity with respect to another quantity, that is, or it may be variation of your one quantity with respect to time. So this is what broadly we discussed yesterday, and then we went ahead with electromechanical instruments. And okay, one important property we also saw here was loading. We want loading effect to be minimum. That is nothing but abstraction of energy for working. We also saw examples, and we also saw why electronic instruments are superior compared to your electromechanical instruments when it comes to loading, because electronic instruments have power supply to work, so they take the energy for working from the power supply, not from the input. These are the properties what we discussed yesterday. Then we went ahead with discussing the basic electromechanical setup. You have something called as a control torque, deflection torque and damping torque. We discussed about control torque, deflection torque, in short it's TC, TD, and damping torque. This is T damping. So this is how, these are the symbols we represented. Mainly the deflection torque is the measurement. Whatever is happening because of the measurement is what we call as deflection torque. But we want that measurement system to be stable, so we provide a feedback system to have a stable pointer indication. That is what is your control torque. And damping torque is, see, the indication is the place where the control torque balances the deflection torque. This is the place where you have the indication. But what happens is, because of inertia, you will have overshoots and undershoots. That is, at one point your deflection torque will overcome your control torque, and at one point control torque will be overcoming your deflection torque, so your pointer will be sort of oscillating. To prevent that oscillations, what we create is what we call as damping torque, which dampens out all these oscillation. And we saw, to create deflection we are always going to use interacting magnetic field. Interacting magnetic field is what we are going to use for creating the deflection. To create control torque, it can be spring control or it can be gravity control. Gravity control can be used only in panel mounted instruments because gravity will act only on the vertical direction, whereas spring control can be used in the horizontal direction, means instruments which are placed along the horizontal plane or along the vertical plane. Clear? And damping torque, there are different ways of producing it. One is friction, the other one is called as eddy current damping. See, here we discuss lot of basic things. So, eddy current damping, remember, it is going to create some extra magnetic field. It is going to create some stray magnetic field. So, eddy current damping can be used if and only if operating magnetic field is strong. See, for eddy current damping is the most easiest way of creating the damping, because this friction damping requires additional setup which is going to make the instrument bulkier, whereas eddy current damping is very easy to create. It just place a small metallic drum or a small metallic disc in the operating field, it will automatically give you the required eddy current damping. Clear? See, how eddy current damping is working, yesterday we saw in PMMC instrument. You have your permanent magnetic field, you have the coil is attached with a spindle, and the spindle has the pointer and also the spring for control. So this is your north and south, and here you have the coil. This is your measuring lead of the instrument. These two are the measuring lead. So when we give the input here, there will be a current that is flowing through the instrument, because of which there will be a magnetic field created here. Now this magnetic field and the permanent magnetic field will interact and try to align with each other, because of which there will be a deflection. Now what happens? The permanent magnets are fixed, so they cannot move. So the coil is mobile, so the coil moves and creates the deflection. As the coil is swinging, it is coiling the spring more and more, so the spring is going to give a opposing force to the deflection of the coil, and we get a stable reading. But what happens is, say for example, this is the place where the stable indication should come. Now this is your 0. So when the pointer is moving like this, what will happen? The spring gets coiled and it starts giving you opposing force. Now because of inertia, your pointer will overshoot. At that point, spring has coiled more than your deflection can balance it, so spring will uncoil and push the pointer back. At this point, your deflection torque is more than the control torque, so again it will push the pointer further. So there will be a oscillation of the pointer like this. This is what we want to avoid. So what we are going to do, we are going to place a small aluminium drum or a disc. Now always remember, only changing magnetic field can create induction. A constant magnetic field cannot create an induction. Now because of the if the pointer is stable at one place, this drum will not see a changing magnetic field, it will see a constant magnetic field. So what is going to happen when the pointer is oscillating like this? It will see a change in magnetic field. Because of the change in magnetic field, there will be eddy current induced here. This eddy current by Lenz's law will always oppose the cause. Always remember, induced current will oppose the cause. That is what is Lenz's law. So as per Lenz's law, what is the cause? Because of changing magnetic field. What is causing the changing magnetic field? The pointer swinging like this is what is creating the magnetic eddy current here. So it will try to oppose this swing and the pointer will settle down for stable indication. This is how eddy current damping works. But always remember, this eddy current damping is going to introduce some stray magnetic field, so it can be used if and only if when the operating magnetic field is strong. This is by itself very important. Here I like to tell one point. You people may be thinking that I am telling you lot of theory, why I should be solving gauge problems directly, but remember, in case of measurements, we are having lot of theory based questions as well. So these all theoretical points are very, very important in terms of measurement. Equally, theory and problem comes from this topic. So these all theoretical points are very important for us to take up GATE or any competitive exam. That's why we are discussing this in detail. Okay. Now, what were the properties of the PMMC? So this is your PMMC setup. So what are the properties we saw here? The operating magnetic field is strong. That means your coil can be made very small. Coil is very small means this system will be very sensitive, because if the coil is the one which is carrying the pointer movement. If the coil is becoming bulky, your pointer system will also be sluggish. If your coil is feather light, your pointer system will be very sensitive. That is what we want. So your operating magnetic field is strong means you will get very good torque to weight ratio. That is, for the required torque, what should be the weight of the coil? It can be very less. That means your torque to weight ratio will be very high. This is a very, very important property we always desire for. The high torque to weight ratio means your instrument will not be sluggish. It will have a very good time response and frequency response. Clear? Then this is what we discussed yesterday. Let us get into the details of the PMMC instrument further. One biggest disadvantage with PMMC instrument is what? Deflection is proportional to average value. Hence, if you apply a pure sine wave, the deflection is going to be 0. This is going to be very important point for your PMMC instrument. So let us so where the deflection is, your TD should be equal to TC. This is the place where we get the indication. Remember this point always. Your control torque, whenever we use spring control, is always given by K theta, where theta is the deflection angle. Theta is the deflection angle. K is spring constant. It may be in Newton meter per radians, or it may be in Newton meter per degrees. So please ensure the unit of spring constant should be in agreement with the unit of theta. Theta may be represented in radians or degrees. It may be represented either in radians or it may be represented in degrees. If your theta is represented in radian, your spring constant should be represented in Newton meter per radian. If your theta is represented in degrees, your spring constant should be represented in Newton meter per degrees. This is very important. Let us work out the deflection torque of your PMMC instrument. The deflection torque will be this is the equation of your deflection torque, NBAI, where N is the number of turns of coil, B is the magnetic field of permanent magnet, A is the area of cross section of coil, and I is the current in the coil. So this is what is your deflection torque. So if you work out TD equal to TC, it means your NBAI should be equal to TC is nothing but K theta. We are assuming that we are using a spring control. So what we will be getting if we balance out, theta is nothing but NBAI by K. That means now for a given setup, when we manufacture this instrument, for the given instrument, once it is created, number of turns of coil is fixed, magnetic field is fixed, area of cross section of the coil is fixed. So NBA is constant. So this NBA in short is called as G. This G is what we call it as galvanometer constant. This is what we call it as galvanometer constant. So theta is nothing but G by K times I. Now look at this. G is also a constant. When the spring is manufactured, the K is also constant. K is a property of the spring. Once we fix the spring, the K is also decided. That means G by K is also a constant. That means if I write this G by K as C, theta equal to Ci, or theta is directly proportional to I. That means we have linearity by design. Your PMMC instrument has linearity. By design, PMMC instrument guarantees you linear behavior. The deflection is linearly proportional to the current carried by the coil. Clear? The deflection is linearly proportional to the current carried by the coil. That is what we are seeing here. The deflection is linearly proportional to the current carried by the coil.